talked about yesterday was how to evaluate an infinite limit using what? What's that little handout?
The order of magnitude.
Just by thinking about the order of magnitude of the functions involved and which one grows faster, right? So you can do some limit, infinite limits like that. So let's look at other ways you can do infinite limits. This is the last section. It is limits that involve infinity. They could involve infinity in different ways, though. So let's see. So let's say we've got this function. This is just kind of a review. The book starts talking about asymptotes in different ways because asymptotes really always involve infinity, don't they? Somehow. They always somehow involve infinity. If you think about what the picture of this is, well, you gotta factor it. Yeah. So if you break this down, you factor it, that's what happens, right? Nothing unusual, and then you simplify it by crossing out that one repeated factor. That's what you get. Once again, is this function exactly equivalent to f?
No.
It's not. Why?
Because it's equivalent to f except for at 2.
This function doesn't have a what?
Hole.
But if you think about f, f is
Well,
the
it has
exact
a
same
hole.
except it does have a hole with it. Good.
No, it
Okay.
doesn't.
So let's just talk about what this function has
Yeah, it doesn't
because
have a
it's
hole.
going to have you review a little bit. So we just said there's a hole because of that repeat. There's a hole at x equals what? 2? What else do we call that hole?
A jump.
In calculus now. It's a discontinuity, exactly. What kind of discontinuity? Can you remove it or not?
There's a removable at 2, but a non-removable at negative.
Yeah, so good. So we also consider x equals 2 as a removable discontinuity. You guys mentioned that it is also, it has another issue, right?
Negative 2.
Non-removable.
But that's not removable.
No.
So at x equals negative 2.
Mr. Walker, to your classroom, please. Mr. Walker, to your classroom.
She sounded mad.
She kind of did.
But that sounded like Mr. Walker, not to me.
Yeah, he's almost always in there.
Okay. So the book is going to kind of review this and talk about it in different ways. I just wanted to go over that again. So where's this function undefined? So Todd says negative 2. Remember, well, think about the definition of being defined. It means when you plug it in, you're supposed to get what?
A number?
Something, yeah.
Okay.
You plug that in, you're supposed to get something. If you plug negative 2 in, what happens? You don't get anything. Why? Because you're on that asymptote. You have a 0 in the denominator, but is it defined everywhere else?
Not at 2.
It's not at 2 either, right? So a function can be undefined in 2 ways. It can be undefined on an asymptote, but when you have a hole, is the function really defined? It's not. I just wanted to emphasize this difference because usually in like pre-calc and algebra 2, we talked about a function being undefined and what did it always turn out to be almost. It was an asymptote, but it can also, when you have a hole, it's still not defined there because there's nothing there unless you have a piecewise function that comes in and like puts a
Fills
dot
it.
somewhere else or fills it in. Okay? So I just wanted to mention that. Let's look at a couple of infinite limits now. So let's say we've got this one. we're really getting down to some calculus limits. These I wouldn't have shown you last year. Maybe we kind of did this one though, I guess. You seen infinity?
Plus 1 plus 1 over infinity.
Okay, so if you try to plug in, you get what? Undefined. Does that mean the limit's undefined?
No, we need to work it out.
I think you just need to think on this one.
When you pull the,
If you take this
do the
limit, can't
of
you write it like
1,
this?
Yeah.
The limit of 1, that part's easy, plus
Yeah.
plus the limit of that. What's this?
1.
Limit of any constant is the constant, right? Just keeps repeating over and over and over and over and over again. It's to 1. And this, remember, you are not, what is a limit? Is it something that you plug in? Yeah, sometimes we're able to like just kind of do that to figure out the limit, but that's not what a limit tells you to do. A limit is this other way of thinking. It has to do with motion. It has to do with as you approach something. So yeah, if you just plug in 0 here, yeah, you're going to get undefined. This doesn't say plug in 0, it says as you approach 0. So you want to think about this as you approach 0. So when you add this is kind of like, let's write it like this, approximately 1 plus, when you do the limit, it's going to be 1 over something. As you approach 0, let's think about something approaching 0, like 0.001, and then square 0.001. Is that thing on the bottom really small
Yes.
or really big?
Small.
Really small. So we've
there's
got
like
1 plus
1
1 over something really small.
Put something really big.
So this part is something really big. This part, if as you approach 0 and you get closer and closer and closer, this part just keeps growing and growing and growing out of control, right? Just like we thought about order of magnitude yesterday. This guy just keeps growing and 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 growing, and the closer to 0 you get, it grows more. So this thing becomes 1 plus infinity, and if you
Which
add
is
1 to
infinity.
infinity, I think it like absorbs the 1, doesn't it?
Yeah.
If you add 7 to infinity, does it absorb the 7?
Yeah.
How about if you add 10 million?
It's still infinity.
It absorbs 10 million like nothing. 10 million is nothing to infinity. 10 trillion is nothing to infinity. Infinity is infinitely large. Okay. This one. Let's talk about this. So what kind of limit do we have here?
We have one approaching from the left.
So we have a left-handed limit, yeah, that way. Okay, so on the top, let's just do this separately. Let's take it apart. So let's do the top and the bottom. So I'm going to do the top and divide by the bottom. We had a limit property for that, didn't we?
I'm sure.
By the way, learning those limit properties is really nice because guess what? The other 2 new operations we're going to learn this year, you've never seen, both do almost the same thing. They let you cut things up in the same way. They have most of the same properties, not all, but most. So it's nice. On top, I don't think we're going to have an issue. If we plug in, we can just kind of plug in 1. We'd really be plugging in like 0.999, right?
Yeah.
But if you just think about it, I don't think there's any issue there, so you can just plug it in and you get what? 2. The bottom, maybe you can plug in, maybe you can't. Let's do it. Let's just plug it in and see what happens. Cotangent of pi, that's 1 over tangent. Let's go cosine over sine. I like that loquacity. What is the cosine of pi? X value over here is...
-1 over 0.
That's not.
Oh, so can we plug in there?
No.
We can't. You good with this? You can circle. Everybody should be able to do this. Okay. So what do I do?
Something tricky.
We could consult a graph. I think this should be easy to graph. We don't have to graph the whole thing. Remember, you just need to figure it out. You just need as much of the graph as it takes you to figure it out. Where are we approaching? We're approaching 1. So if we do cotangent, the period
It's 2.
tangent and cotangent have a period of pi. Divide by pi, so you get 1. So if you do cotangent, this first asymptote is at 1. What's cotangent look like?
It's like x cubed, isn't it?
It's like x cubed, that's tangent.
It's
Like negative
tangent.
x cubed scooted over this way, right? So, what is it?
No, it doesn't exist because no, negative infinity because you're approaching to what?
Where's it get negative infinity from? Because we're approaching 1 and we're writing on this way.
Yeah,
It's going
so it's
down to
going to
negative infinity. So it's that. And what is that?
0.
0. Why is that 0, Brett?
Big number on top and really big number on the bottom. Small number on top.
If you're unsure and you're still having trouble with this argument, go back and just think about it as finite numbers, okay? Think of this as like 2 over 10,000. What's that really close to? It's really small. It's really close to 0. If you go all the way and you actually try to get to -1, when you do the limiting process, this just keeps growing and growing and growing, and finally it eventually gets to infinity, which means this eventually gets to exactly 0. What I don't want you to think of is this limit just like stops somewhere. It keeps going and going and going. So it's not like do we need an approximately sign here?
No.
We do not. We do not need an approximately sign. It is exactly 0. And that's the nice part. That's the thing that makes everything work with all of our technology, is that you can do things like that. So useful. Okay, good stuff. Do we have one more? Yeah, maybe 2 more. Let's talk about when we can use the stuff we learned yesterday. Because could you use the stuff we learned yesterday on this problem, for instance, order of magnitude, on this problem right here?
No.
Why not?
Because technically there's the plus.
You'd learned something about power functions yesterday, so I think you might even be able to think about it on the top, but did we learn about cotangents?
No.
So you can't do it on that one, right? But,
Did you?
how about this one?
That was close.
5. I mean, this is number 4.
Whatever. You know my numbering is just always right on. I change stuff. Sorry.
Sorry.
Let's try that. Now we'll do one more. Okay, you can do this different ways. In college, they never liked my AP thinking. But I was still right all the time. So,
What's the bottom one?
I'm going to do this with AP thinking, which is better in some ways. Let's do it with growth rates. What's growing faster?
The bottom one.
Yeah. What's the order of magnitude on the top? You can actually do orders of magnitude, like for each function you can say the order of magnitude is this, or 3, or 7, or a natural log of 2. You can find actual orders of magnitude. What kind of function is up here? Quadratic. It has a quadratic, has a polynomial order of magnitude of 2. This one has a polynomial order of magnitude of 2.
So they're the same.
So what do you think the limit's going to come out if the order of magnitude are the same? Do we
1.
have one like that? What happened to the picture? Remember that one that
It
looked
just,
like
it
this?
just like it leveled out at 2.
It leveled out at a certain spot. So the only question is, we know this is going to level out. Where's it level out at?
Is there a quick way to figure this out?
Oh yeah. If they have the same order of magnitude, you know it's going to level out. We talked about that yesterday, right?
Huh.
The only question is, where's it level out at? All you got to know is the asymptote.
Number 7.
What's the asymptote for this kind of case? Because that's what it levels out at. Right?
So it'd be
Connecting the
a
dots?
horizontal asymptote,
It's a
right?
horizontal asymptote.
So it'd be something.
This has a horizontal asymptote because it's the same degree on top, it's the same degree on bottom. That's what we learned last year. So what do you do in that case where it's the same on top as on bottom?
Is it
Would you
leading
put
coefficient
3
over
over
leading
7?
coefficient?
You put 3 over 7. So that's what the limit comes out to as well, because it goes and approaches that asymptote. Are we starting to connect some dots here now? So you can think about it as an asymptote. You can think about it as magnitude growth. You can do it another way too. So let's do it another way. This is the way they always like to teach me. For whatever reason, I thought it was the least effective way, but whatever. Takes more time for sure. You can multiply by a clever 1.
Oh.
What clever 1 would be nice?
Why would you?
I showed you guys this last year, didn't I?
Oh yeah.
You just take the biggest thing, you pass it inside.
But why would you do that when you have the easy way? Because.
Well, it's another good way to think, and sometimes only one of those ways will work. So, I don't know. I got blasted for not doing it this way, though, I remember. My particular teacher, so. Do you do that here and you get 3?
Plus 2 over x.
plus 2 over x.
We did this last year.
Yeah, we did. Can you guys see how many ways you could get this problem right? 7 plus 4 over x minus 5 over x squared. You've still got the limit, see? It's still there, I haven't used it. Now when you actually plug in infinity, now what happens? These parts all go to what? 0. All of these parts go to 0. What's
I have
left?
a question.
Yeah.
Never mind, I got it. I think.
So this way is kind of like the simplest way, you know what I mean? Because all it requires you to know is that this goes to 0, right?
Yeah.
That's the only new thing which we just talked about. It's not like that big of a deal. So it is kind of like the simplest thinking, but I don't know. I think it's good to have all those tools in your bag and you use which one you want. So, because sometimes this might not work. You might need to think about magnitude or something. So, see you one last problem. It's another infinite limit. Answer.
Wait, oh gosh.
You gave us examples of the rules, what happens with
Is it infinity?
top?
Yep. It's infinity y.
Bigger order
Top
of
is
magnitude on
faster.
top.
Bigger order of magnitude. It's growing faster. Yep.
So there's like infinity over 1, right? So then it's infinity.
Yeah. It's growing faster on top, bottom line. If you think about this as like what we learned in pre-calc, this has, does it have a horizontal asymptote? No, because degree on top is bigger than degree on bottom. It's not going to have a horizontal asymptote, so it's not going to go to some specific number. So it's either got to be infinity or like undefined or something. But that's the easiest way to do it. Could you do it like this? Yeah.
Yes.
What would you have to multiply by on the top and bottom?
X
X
cubed.
cubed.
X cubed?
1
1
over
over
x.
x.
1 over x cubed, and then you'd find the same thing if you did that. Okay? Alright, I think we're done.
What if you had 7x cubed on the bottom and then 10x squared on top? Can you still do the clever form of 1?
Yeah.
And then
It wouldn't matter what was on top and bottom, we can always do this.
Okay.
Are you ready?